Okay, so time keeps moving on. This is class 33. Anybody know how far we get? How many classes there are?
35, right?
No, there's more than 35.
I
know.
We're getting close though.
I know there's 2 more.
41.
There's 2 more.
We get to 41.
And that's explained.
So homework 12 is posted, and that's got 9 problems. So that's more than the last assignment, but they're relatively small problems. And I think you're going to see from today's class that this is pretty straightforward stuff. I told you earlier that the peaks of the course in terms of complexity was external rate of return. What was the other one? Did I say, I think it was maybe economic service life are the 2 most complicated things in the course. Cost estimation definitely is not. So maybe your brain could use the break. So homework 12 is due next Monday, and then Friday of next week is the project. So I hope that's going well. Any announcement questions before we start talking about cost estimation?
So we're not gonna have to present the project at all, right?
No, we wouldn't have time for that.
Okay.
Yeah. So just the assignment deliverables that are mentioned on the handout itself for the project. Any other questions? All right. So cost estimates, it's simpler information, I think, simpler calculations than some of the stuff that we've done, but absolutely important when you consider how the data is used and the effect it can have on people. So, for example, when organizations are estimating what costs may arise from different projects, it could be that a municipality is deciding whether to make improvements to a fire station or a hospital. And if you get the cost estimates wrong, then it may not be possible to do either if they begin the project and then realize that the funding doesn't exist to complete it. So it's really important to get it right. And if you look at individual features that could be included in a building, whether to include a defibrillator or a wheelchair lift. Remember, we've talked about how there are budget limitations for almost every organization. And maybe the only time that wasn't true is when anybody seen that movie about the atomic bomb? What was that? Oppenheimer. Yeah, those guys seem to have unlimited money, but that's the exception rather than the rule. So it's important to know how much stuff is going to cost so that you can accurately plan for features to include in a project. So our textbook offers some pretty important information about how estimates should be generated and the way to be consistent and ethical. And the first piece of information there is that cost estimates should be based on sound information that's gathered over a wide range of conditions that are representative of the current situation. So for instance, if we had construction cost data for West Virginia, it wouldn't be appropriate to use that cost data in Alaska, because Alaska has a different climate, it has a different geographic location, and for a variety of reasons, it's likely that construction costs in Alaska are going to be different than the situation in West Virginia. And the same thing is true in just about every circumstance, that you're never going to have exactly the same conditions in one project or one location compared to another, but there are a variety of things that we can do to manage those differences, whether it's the passage of time we're accounting for, or differences in size that we're accounting for, or location. Those 3 things can be corrected for, but we have to just be cautious of extrapolating data over non-representative conditions. The second key point is that we should use accepted theory and techniques in taking statistical samples, building budget elements, and drawing conclusions. So sometimes people are tempted to invent their own method for coming to an answer, and this is not one of those situations where you should take liberty of making your own method for cost estimation. You should use accepted theory and techniques, a way that is going to be justified and recognized by the people who check your work. And the third point here is to keep personal and working relationships separate when making estimates. And that's pretty different from the other 2. The other 2 are more related to analytical techniques and technical considerations, but now here in point 3, it's kind of bringing personality traits or maybe conflicts of interests into account. And the reason there is that it's often the case that people who do a lot of cost estimation have interface with product suppliers, and sometimes the line can get blurred between getting information from product suppliers and, say, a meeting that can turn into a business lunch, that can turn into just situations where the material suppliers have an incentive to get you to purchase their products, and will give you swag or freebies or meals or things like that. So it's important to avoid bias and just make cost estimates on the basis of the actual quality of the materials and the cost of the materials and nothing else. So just as an illustration of one method for developing a cost estimate, I wanted to tell you about a research project that I did a few years ago where we were studying the effect of hydraulic scour on streams. And so that's just when, here in West Virginia, we have really steep topography, obviously. And because the watersheds are so steep, the water goes through streams very quickly. And fast-moving water velocities can erode the foundation that bridges are built on. So it's a little bit hard to see in this picture, but this concrete bridge abutment is built on rock, and the rock that's underneath this concrete piece has been scoured away by the river over years. And so if there's a little broken off bit of shale, then when there's fast-moving water, it will just carry that shale downstream and over time erode the foundation under the bridge. And that's obviously dangerous for the strength of the bridge and the load it can carry when there's heavy traffic going over there. So the project was to study the relationship between historical stream conditions and the quality of rock. And so Marshall was leading the research project, and we hired some external partners to do core drilling so that we could get rock samples. And so what we had to pay them was a mobilization fee to get all their heavy equipment on site to do the drilling. And so that was just a flat fee that they charge even before they start drilling, just to get everything in position. And then we had to pay a certain fee for each day that was having to do with the maintenance and protection of traffic. So you can see that there's cones on the road. Anytime you go to a work zone, you'll typically see cones and maybe somebody holding a sign. And so when you're trying to determine how much is it going to cost to get these rock samples we need, a part of the cost estimate was the mobilization. Part of it is related to traffic protection. Part of it is to have a geologist on site to record and log all of the samples that are be coming up, to wrap it in plastic film. And so now you're thinking about the supplies that you have to have, whether it's something relatively inexpensive like the plastic film or the cases that you have to build to hold the samples, storage for the samples in a storage facility, mileage for the geologist to drive to the site. So some of those things are on a per unit basis. Like the geologist is being paid per hour of time on site. The reimbursement of the geologist travel is per mile from their starting station to the job site. So all these costs add up over time, and we can break costs into two main categories. The first is direct costs, and we've talked about this a little bit before when we were discussing the price-demand relationships. But direct costs can be allocated to a specific output or work activity. So you can know, for example, how much sugar it takes to make a package of Twinkies, or how much plastic is used to package up the Twinkies. And so you can answer the question, how much of a certain material does it take to make the output? So, for example, in the case of a job like this, you know how much fuel is burned by the vehicle that travels to the job site. Or you may know, like, what's the limit in terms of this drilling rig? It's velocity of drilling, the number of core samples that are needed. You could say how many hours the drill rig is going to need to be on site in order to generate the rock samples. So those would be examples of direct costs. Materials, labor salaries, production expenses. But indirect costs are those things that don't have a direct relationship with what's being produced. So sometimes indirect costs are also called overhead costs. And because it's hard to say exactly how much of these indirect costs is required for the output, instead of even attempting it, we just use a percentage or some sort of a factor to account for them. So, for example, we used computers on that research project, but when we were doing our budget estimate, we didn't take into account how many hours of computing or how much accounting services was needed to keep track of all of the different moving parts of it, or the rent of a building that has a factory in it. You can't say exactly how many dollars of rent is needed to produce what's coming out of there, but you just account for all of that in a lump sum factor. And here at Marshall, the indirect cost recovery percentage is 48%. So when you bring in $1 for research, 52 cents of that is available to the researcher to do their work, and 48 cents goes to the university to pay for things like the building, the administrative parts of managing the grant, the electricity, and other related factors. So direct costs and indirect costs. There's a question on the homework assignment where I ask you to consider these two definitions and then classify a list of different expenses into the two categories. Okay, so also on the topic of cost estimation is a discussion we need to have about the two main techniques for generating cost estimates. And these are two very different mindsets. The first kind of approach is when you don't necessarily have to be super competitive, where you're selling something that's relatively unique and the market isn't saturated with whatever it is you're selling, and where what you're doing is adding up the cost of the different things that's required to make the end product that's being sold. So for example, when we did that research project, we were using the bottom-up approach because we made an estimate of how much time of the researchers was going to be required. We made an estimate of what equipment costs we were going to have. We made an estimate of the subcontracts that we'd put out for the drillers and so on. We added on the indirect costs, and then that told us the total cost that we needed to charge for that research. Now, since we were doing it as a nonprofit organization, we didn't add on a profit factor on top, but a company that was taking this bottom-up approach would add up all of the expenses of the thing that they're trying to make and then factor on a little bit more that they want in profit on top of it all. So sometimes if you read reviews of new mobile phones, they'll sometimes make an estimate of how much the individual components in the mobile phone costs. You know, they'll talk about the cost of the display, the cost of the battery, the processor, the radio, and so on. Add it all up, and then the manufacturer thinks about how much profit they want, and then they decide what price to sell the item for using this bottom-up approach if they're selling a relatively unique thing where there's not a lot of competition. So probably, you know, when they're pricing an iPhone, Apple is the only manufacturer that uses that operating system and the App Store, so they have somewhat of a monopoly when it comes to a particular product that they're selling. And so they might use a bottom-up approach with a little bit of information from the other technique, the top-down approach. In the case of the top-down approach, what you're doing is you're thinking about the competition, the other people who are selling your item, and you're thinking, what is a good target price that I want to sell this for? And then once you know what you have to be able to sell the item for, then you allocate all of the individual components as a portion of that target cost. And so in the case of like an Android phone, where you could get one from LG, Samsung, Motorola, there's lots of different Android phone manufacturers. They kind of know what price point they're trying to go for, and then they decide how nice of a display, how fast of a processor, how much memory to allocate based on making small changes to the budgets that comes up with the direct costs. They factor in their indirect costs for the things like advertising, management salaries, and so on. And then allowed profit, depending on the industry, may be relatively large, may be relatively small, but the main idea is some competitive price is what the starting point is, rather than being the finishing price, the finishing point um, of the cost estimate. So the biggest difference of the two techniques is that in bottom up, the price that you're going to sell the item for is the final part of the calculation. Whereas in the top-down approach, the price that you're going to sell the item for is the starting point rather than the finishing point of the calculation. So any questions about the two techniques or the differences between them? Yeah.
Are these only used for something that has one large price, such as a single service or project, or can these be used for producing a certain amount of products, where each one has its own little price?
Right. Yeah, that's a good question, because I think that what makes things even more complicated is that the more you're selling, your prices are probably going to change, right? So in the case of an Android phone that's really popular, they probably are going to be able to get memory cheaper for it or the display cheaper than if they're selling very few. So I don't think that either of these is used in isolation ever. I mean, I think even when they're doing the bottom-up approach over at Apple, probably somebody somewhere is thinking about the competition on the Android side, because if the price is too high, then people would switch. So I think that elements of these ideas are used in every situation, but I don't think there's ever going to be a case where you're just purely doing bottom up or purely doing top down. Other questions? Okay, now here's a completely different idea, unrelated to what we've talked about so far, but this is an illustration of diminishing returns. Probably a concept you've heard of before, diminishing returns. It means that if you work on something for a day, you'll accomplish so much. But if you work on it for 2 days, you may not accomplish twice as much. That the overall value tends to go down the longer you spend on something. And so this is talking about trying to prepare a cost estimate specifically. And what it says is that you can spend 10 minutes preparing a cost estimate, and it'll be accurate to maybe plus or minus 30%. But if you spent an hour on it, so 6 times as much time as the first estimate, so maybe you're getting better data by calling more suppliers, or you're breaking the problem up into smaller pieces and you're getting prices on individual sub-elements. So rather than, like, sometimes in construction they'll just say how many square feet is it, and if it's like a new construction residential, they'll say $200 per square foot, so the cost estimate's just based on that. That would maybe be a 10-minute estimate if that's all the detail they went into, was calculating the square footage and then multiplying that factor. A 1-hour estimate maybe would ask, well, is it going to have tile in it or is it going to have carpet? The 1-hour estimate maybe would ask, is it going to have wallpaper or paint? Just a little bit more detail will improve the quality of the estimate, bringing the inaccuracy down to plus or minus 20% instead of 30%. But as you spend more and more time, this curve is getting flatter, which means that you could spend an infinite amount of time preparing a cost estimate, and it probably wouldn't be that much more accurate than if you just only spent 3 weeks on it. Because this is approaching kind of a cutoff point where the line becomes completely flat, and there's just some inherent inaccuracy due to market fluctuations where you can't know everything about what the costs are going to be, so there's always going to be a little bit of plus and minus on your estimate. So this is just the declining rate of improvements to accuracy over time. So this is an important concept, but what you should keep in mind is you wouldn't want to spend 3 weeks on a cost estimate for a relatively minor project, because if you spent 3 weeks, that's taking time, and your time is costing money for your company or the client. And if you could get an estimate that's almost as good in just 1 week, then it's likely that the extra amount of money that you spent getting an even better estimate isn't saved by the improved data. So the idea is just sometimes good enough is good enough. Like a 1-day estimate for a project of medium size. Like for instance, I had some contractors come to my house a few years back and do a cost estimate for how much it would be to put a new driveway. I have a relatively long driveway and it was breaking up. I wanted to switch from asphalt to concrete. So one guy just drove up and just kind of eyeballed it and gave me a number, and I didn't have a lot of confidence in that. The person who came out with like a wheel that measured the length of the driveway and then asked me how thick I wanted the concrete to be, I felt like that was probably a little bit more of a reliable estimate, that it wasn't just being pulled out of thin air and like excessively high. But if somebody had come out and they'd wanted to like measure the number of grains of sand that was going to go into the concrete, and like if they were overanalyzing it, then I'd also not have a lot of confidence in that, because I'd think that they were spending so much time on the cost estimate that they'd have to build all that time into the cost of my driveway, and it's unnecessary to count the grains of sand that are going to go into the concrete. So I think that gives you an idea of the main concept here is just pick the quality of the estimate that aligns with how much accuracy you need. Okay, now this series of curves is really important, and experience has told me that unfortunately most people don't ever quite seem to understand this concept. And I usually ask about it in the final exam. So I hope that this semester people will understand it and think about it, because it's really important. There's three different curves here, and I'll talk about each one of them. The first one, potential for life cycle cost savings. First of all, life cycle is just the idea that when you own something, it incurs costs from when you even start thinking about the project to when you construct it, when you're using it, and when you dispose of it. Each one of those stages has costs associated with it. The planning stage, the production stage, and the disposal stage. So early on, at the beginning of the project, you have the potential to save a lot of money because, for example, you may make a decision that allows you to eliminate unnecessary features if you're careful in your planning. If you're kind of reckless and you're not paying attention to details and you fail to make those cost-saving changes, then once it's built, you've lost the opportunity to make those changes. So think about a new academic building on campus. If people aren't very careful when they're making their initial plans and they just decide out of thin air, we're going to make the building 4 stories tall, but they really haven't thought about what's going to be on those different floors or why they need a certain amount of square footage. Once they make it 4 stories tall, no matter whether they use economy toilet paper or cheap carpet or LED lights instead of fluorescent lights, all those little cost-saving measures that they take later on don't have as much importance as if they had just decided on a 2-story academic building instead of a 4-story academic building. So this curve just illustrates the trend that the longer you go in the product's life cycle, the harder it is to save money. And towards the end, think about the building has been constructed, it's been used over time, and now it's just the demolition phase. There's very little you can do to save money at the demolition phase. You can take the rubble and take it to a landfill, or you can dump it in the river. Like one of those is cheaper than the other, but they're both representing only a tiny fraction of the overall cost of the component over its entire life cycle. So that's the first curve, is the potential for life cycle cost savings. Now, this curve, a cumulative committed life cycle cost, is just the idea of not how much have you spent, but how much have you planned on spending. So during the needs assessment phase is when you're just doing like engineering work and planning work. So it's just mental work, but just by making decisions one way or the other, you're committing yourself to a certain cost. So during the needs assessment, if they decide on a 4-story building instead of a 3-story building, then they've committed themselves to a certain cost, even before they've done the preliminary design. So that's why this curve, the committed life cycle cost, leads the cumulative life cycle cost, because the cumulative life cycle cost represents the actual spending that has occurred, whereas this leading curve before it is more about the planning for the spending. So when does the planning for the spending occur? And what you'll see is that here during the acquisition phase, when they're doing detailed design, is where this is the steepest. So when this line is really steep, that means that the decisions are being made so quickly as to how the money is going to be spent. And then when this tapers off and becomes more flat, that just means that they're not really making any more decisions about how the money is going to be spent. And then this is actually, the steeper the line is when the money is being spent, not just when the decisions about the money is being spent. So I'd encourage you to think about this and try and, in your own words, explain it, because you'll probably face a scenario in the future where you'll need to explain one or more of these ideas that are represented in this figure. So the main idea here, cost savings are easiest to obtain early on before too much money has been committed to a certain course of action. By the way, any questions about this figure before we move on? Okay. Now, the first quantitative method we're going to talk about today for producing cost estimates is the unit method. And it's really simple, simply because what you do is you figure out the cost per unit of something and how many required, and then the total cost for that category of components is just the unit cost multiplied by how many are needed. So this is used pretty commonly when you're doing a budget estimate that's involving mileage reimbursement, or highway construction, or constructing a house. You can just see these are some kind of rule of thumb unit costs that then you would multiply by the number of miles driven, or the number of miles of highway that's required, or the size of a house in square foot, or the volume of concrete per cubic yard. So the unit method is just applying the given data in terms of the unit costs and how much is needed for a certain component. So this is the first part of our in-class exercise. Let me hand these papers out to you. So in this problem, there's 1,500 sections of a gas pipeline that are being constructed. Okay, so it's just as simple as multiplying the cost by the number of things that are needed of that category and adding it all together. I encourage you, though, even though you probably could solve this entirely in your calculator without writing anything down, the disadvantage of that approach is that then whoever's looking at your work can't follow along as well as if you write all the units and descriptions of the categories. And so I'd encourage you to, take a systematic approach in writing your solution, just not only so other people can understand it, but also I think will help you to avoid mistakes if you see that, for example, the units work out the way that they should. Hours per section multiplied by the number of sections multiplied by dollars per hour gives you dollars in the end. So being dimensionally consistent and also documenting the solution, I think, is a good idea. So any questions about this first one before we talk about cost indices? All right. Well, let's talk about cost indices. There's a lot of different sources of data out there that will tell you how expensive things are now compared to how expensive they were in the past. So let's take a look, for example, at a construction cost index that shows how much single-family homes have cost over time. And what they're saying here at the top, and maybe it's hard for you to see, but they're saying in 2005, they're saying that the cost is 100. So what that means is if the cost was 100 in 2005, you can see in January, 1965, the cost was 12.7. So that just means that a new single-family house back in 1965 only cost 12.7% of the cost in 2005. So it's a linear expression or a ratio that you can use to find out how much things in the past cost compared to today, or you can find out, if you extrapolate into the future, how much things are going to cost based on the trend of index data over time. So remember that said that 2005 was the baseline year, where they're saying, just by definition, let's say this is 100%. Now, the average family home wasn't $100, it wasn't $100,000, it was whatever it is. They're just saying that this is the index year. And so you could see that in 2022, the cost was 181, and that went up a lot from 2021. In fact, the prices have just really skyrocketed since 2012. It was still below the index, 98, but then it went from 98 to 181. So a lot of people complain about house affordability, and it's easy to see why when you look at the index data. So that's for construction of single-family homes. And by the way, you're going to use this on the homework. There's two different pages to this index. One of them is for constant quality construction, and the other page is for price deflator construction. And we won't use that second one. It's more related to if you take into account people's changing preferences over time. This is more like on a square foot basis and constant quality, constant sizes. So we'll use this first page on the homework assignment. But the idea with that is there's a variety of different data sources where if you want to know the cost in a certain time, you just multiply it by the ratio of the indexes that you've got. So the index for a certain date divided by the index at the date where you have the original cost data for. So the way to look at this is basically the cost, for example, today will be the past cost multiplied by the ratio of the index today to the past index value. So it's a simple idea, and we'll use this approach for the next part of the in-class exercise, with the difference being that we're going to be looking at individual components, not just the whole thing. We're going to look at three different categories for that in-class, the second part of the question. So, by the way, on your paper, I didn't update the first place where it says a repair garage was built in 2004. Change that to say 2014. So a repair garage was built in 2014 for $650,000. That was the total cost. And what we know is what percent of the total cost were certain categories. And we also know what was the index in 2014 and 2023 for each of those categories. So what you should do is, in part A, calculate a weighted index by having it be 30% 175, 20% 145, 50% 135. So that's part A. Do the same thing for part B with the current year cost index data, and then estimate the total cost. Again, I forgot to update the dates. It's 2023 and 2014. If you can change that in part C as well. So we want to know what's the construction cost in 2023 based on the data from 2014.
That will also be true for part D. I assume it's got 2004 and 2008 as well in the note.
In the bottom. Yeah, that's right. So what we're going to try and do is calculate the weighted index, because we know the index of each category, and we want to know overall what was the weighted index, and then use that ratio of index data with the past cost to predict what will be the future cost. Okay, so the index back in 2014 should be 149. If you do a percentage weighting of each of the different categories, so we know that the labor 30%, so 0.3 times the category index of 175. 20% of the costs comes from materials, 50% of the cost comes from equipment. So the weighted cost average in 2014 should be 149. And then in 2023, the weighted index should be 178.5. So if the percent of the categories holds true over time, then that means that the cost in the future, in 2023, is going to be 178,691. Because we just multiply the old cost by the ratio of the indices. And then if we take that overall cost, we can find out what are the category costs by multiplying it by the weighting. So we can find out how much of the overall cost is going to be labor, how much is materials, how much is equipment, and so on. Okay, so the homework assignment is going to be pretty closely related to these first two problems. There are a couple of things that we'll discuss on Wednesday that are on the assignment. So there won't be every question that you're in a position to answer yet unless you go to the book and learn about the learning curve and cost capacity equations. But several of the problems are pretty closely related to this. So if you want to get an early start, you certainly can. Remember that the next assignment's due on Monday, and then Friday of next week is the project. So that's it for today. I'll see you on Wednesday.